The last 2 days are symmetric one, and I want to provide certainly numerical evidence that there are non-symmetric ones for the full Euler equation. First, a list of co-workers. This is part of a general project supported by PSRC involving the University of East Anglia with Emilien Parot, involving Bath with Paul Mileski, also Philippe Guyen as a visitor. There is a student also who did some calculation, Tao Gao at UCL. And of course there is Zhan Wang. This name is in red because he is responsible for a lot of the numerical calculation that we did. As you'll see, these are very delicate calculations, not so much in writing the codes, but in using the continuation methods, in finding initial guess in the Newton methods, and he did, as you'll see, very outstanding amount of work on that. Oops, wrong way. So there will be, as indicated in the title, gravity-capillary waves, as we've seen a lot of them in the previous talk. But there'll be also hydroelastic waves, which are waves under a nice sheet or a membrane, and of course we've seen also quite a number of them in previous talks. In the first part that we're going to do, we're going to talk about two-dimensional waves, and then after that we will in fact present a lot of results for three-dimensional waves. So there's a picture that you've already seen in fact in the talk of Emilien, trying to illustrate the configuration. We have there a layer of water bounded below by an horizontal bottom. Also in most of the calculation we're going to do, everything will be in infinite depth. And here we have the elastic membrane. On top we would have the atmosphere characterized by a constant pressure. And on that membrane we might have some disturbance which is moving, and it's going to generate waves in the problem, and these are the waves that we want to study. In the problem of gravity-capillary waves, then there is no elastic sheets, and we just have an interface between water and the air with the usual jump in pressure proportional to the curvature of the free surface. I'll give the wrong way. Well, of course, the water will be assumed to be incompressible. We'll have irrotational flow. And in the talk, in fact, we're going to neglect the effect of viscosity. A lot of these waves that we're going to study will be studied in a frame of reference moving with the wave. And in such a case, we have a steady flow. But we will mention, as time permits at the end, some unsteady calculation to discuss a little bit the stability of these waves. Something we've seen many times over the last 2 days, the basic equations. We have a potential function phi satisfying Laplace equation. We of course have here the classical kinematic boundary condition. There's no time appearing. I'm putting now in a frame of reference moving with a wave. The usual dynamic boundary condition. This condition, if we have a bottom, the kinematic boundary condition on the bottom. In the case of the elastic sheet, we have this extra term, which is here in blue, that we've seen often. D is the flexural rigidity, and we have here, we're using the model developed by Plotnikov and Toland to describe the elastic sheet, as was done, for example, in Emilien's talk. Kappa is the curvature. So here the cube is a curvature. Here we have the second derivative of the curvature with respect to the arc length. In the case of gravity-capillary wave, of course, that blue term is not present, and it's replaced simply by minus the surface tension divided by the density multiplied by the curvature. So mathematically, all these problems is just these type of equations in which, in fact, in the dynamic boundary condition, we have higher order derivatives which appears. In the case of surface tension, it's just the curvature, it's second derivative, but here it's the fourth order derivative which appears in that equation. Now, in this type of problems, we're interested in studying waves. And the usual waves that we know about these problems are, of course, periodic waves. Oops, going the wrong way. Periodic wave would have a train of periodic wave extending from minus infinity to plus infinity. And as you take a wavelength, which get longer and longer compared to the depths, you can get solitary waves. The basic solitary waves, the most well-known solitary wave is, of course, the one that we have in the absence of surface tension, in the absence of the elastic sheet, and these are the waves which are described by the quarter-wave-de-Vries equation for sufficiently small amplitude, but they exist also as solution of the four-water wave equation. If we now put either the surface tension in the problem or put the elastic sheets, there are also type of solitary waves which can exist. The first kind that we have there is a solitary wave with a train of ripples in the far field, ripples of constant amplitude. This is not really a solitary wave because it's not flat in the far field, and that's often referred to as being a generalized solitary wave. We're not going to talk about generalized solitary wave here, but we're going to more focus on these two types of solitary waves, which are in fact solitary wave with oscillations in the far field, but decaying oscillations. And we heard about this wave in previous talks, in Emilian's talks, in Akila's talk yesterday. They can exist both in finite depths and infinite depths. In fact, for simplicity, we will concentrate in the rest of the talk to infinite depths. And we have these waves. And one which is like that, which has a kind of a crest here, naturally we call that an elevation wave, and this one we call a depression wave. So just to fix the idea, we put some dimensionless variables in our problem using the surface tension and the gravity, and we have some parameters that will appear. One of them is, of course, the speed at which the wave is moving. And another one is something which we measure the size of the wave, how big it is. So, for example, in the previous picture, when we had the elevation wave and the depression wave, we could take, for example, the elevation or the ordinates of the crest, which would be positive for elevation wave and negative for depression waves, as a measure of the size of the waves. Now we're going to get to non-symmetric wave. That's not a very good choice because we don't have the symmetry, and therefore there are different things that we can do. But what we use as a parameter to measure the size of the wave is the energy of the wave. We see as a kinetic energy, potential energy due to gravity, and the potential energy due to surface tension. So let me see what I have there. Now let me first come to this. This picture will be in water of infinite depths, and all the solution that I show, all the sketches of the wave that I saw on the previous transparencies were waves which were symmetric. So there was always possible to find in the problem, like here, a vertical line so that the wave is symmetric with respect to that line. And all the waves that we've seen in the previous talk today were all symmetric waves. And what we like to do in this talk is to show that in addition, there are many different families of waves which are in fact non-symmetric. And in doing that, the idea is that we solve the problem essentially by boundary integral equation methods, discretize the problem, and solve by Newton iterations. The hard part in the problem is to find and to cook up an initial guess so that we can move onto a branch of non-symmetric wave. That is a first hard part in the problem. As soon as we get a solution, then we can construct by continuation the whole branch of solution which goes through that solution. Simply taking a solution that we obtain and then using it as an initial guess to compute a new solution for slightly perturbed values of the parameters, and like that builds a whole branch of solution. And that's also very delicate because there are, as we'll see, many solutions which are very close to each other, and it is quite a delicate problem to do that. Infinite depths, I'll remind that we're going to put infinite depths. We're talking now about the gravity-capillary waves. I'll say a few words about the hydroelastic waves a little later. And, well, first, these are the basic type of solution, the elevation wave and the depression wave. And we can then describe them here in this picture, in which we put on the horizontal axis the speed, the dimensional speed of the wave, and in this picture that we have here on the vertical axis, the amplitude. So the displacement at x equal to 0, positive for an elevation wave and negative for a depression wave. As we had in a number of talks of Achilles, of Emilian, we know that these basics, still talking about the symmetric wave, that these waves bifurcate from the minimum of the linear dispersion relation, from this point at which the group velocity is equal to the phase velocity, and because of the dimensionless variables that we put in our problem, then this point is in fact c equal to square root of 2. This is just this point. It's not very readable in here, but it's just square root of 2. And then we have the branches of solutions. Now here, the amplitude here is negative. This is a branch of depression wave bifurcating from square root of 2. And it's a rather dark curve. It's a monotonic curve, which bifurcate from that point. The curve that we have for the elevation wave is much more exotic. It has a lot of oscillation. It bifurcates from square root of 2, in moving like this, and then in moving here. It has a sharp turning point here. So these computations are quite delicate to make the turn in here by continuation method, and then it goes like this, and then it would continue. So it's a complicated curve that we're getting there.
Where does it go after the purple part stops?
After the green part there?
Yeah.
It would need more and more mesh point to compute, but it would probably continue to.
Not go back down.
No.
But these loops are associated with increasing complexity. And
Yes, it increased complexity, as we see on profiles, yeah. So you need more and more mesh points when you want to calculate them. These two-dimensional calculations that were done are a delicate calculation for the non-symmetric wave and required a very large number of grid points. Some of the calculations were computed with 6,000 points, some of them with 10,000 points. Yeah.
Where on the branch does the wave stop being symmetric?
So far, all the waves are symmetric.
The whole thing there?
Yeah,
okay.
We're going to move. Now, how are we going to do that? The idea to get non-symmetric wave is because first...
Can I ask a question?
Yeah.
Are there any secondary bifurcations you detect along any of this branch? Or is these all a clean branch?
There are, you will see that the non-symmetric waves, in fact, bifurcate from the symmetric waves.
Right.
So there's all kind of bifurcations, yeah.
Do we see those points yet? Oh, A, B, C, D, E, F?
No. What we're going to see in here, looking like you can have, for example, here A and B, basically an elevation wave and a depression wave, which are in fact traveling at the same speed. Now, because of the complicated behavior that you have on the elevation waves, then you can get also two elevation waves which travel at the same speed, C and D, and E and F. And with that, we can build non-symmetric waves. I mean, I'll put some reference later. To build it, as I'll indicate in a minute, by using A and B, using a depression wave and an elevation wave. This was done before for model equation, for example, for the fifth order quarter-wave de Vries equation. But we can do it, we generalize that to do it for the full Euler equation. And this complicated structure to have the thing to turn around is something that you get with the full Euler equation. So, for example, to be able to superpose and to build a non-symmetric wave with E and F is something that we can do with the full Euler equations and not with model equations. So yes.
Sorry, I have another question. For the bottom branch, does it keep on going, or do you have a lowest kind of extreme wave?
The depression wave, if you continue to do them, would then go to configuration with a bubble.
Okay.
Yeah, so it
That's
would.
not part of the branch that you.
No. We just concentrate, in fact, rather close to the bifurcation point, rather close to square root of 2. So what we would do is to take, in fact, we have two waves, like A and B, for example, or E and F, two waves which travel at the same speed. We're going to take these waves and, in fact, glue them together, and with that build a non-symmetric wave. Of course, it's a nonlinear problem. You cannot superpose things. So what I mean by that is that we're going to glue together two waves like this, and then use that as the initial guess in the Newton iteration. And then it turns out that the Newton iteration converge, and the result of it is a nonlinear, non-symmetric waves. Now, what do we get on this? This is a similar picture, but now with the energy versus the speed. And the blue curve here, this is for the depression wave, and the other one, the elevation wave, is again this complicated structure, these oscillations that we get there. Now, I'll put here a number of reference of people computing non-symmetric waves, essentially by superposing, what I'm completely lost there, by superposing two solutions like the solution A and B for equation like the fifth order KEV. For example, the work of Young and Aquilas is using exponential asymptotics to construct this wave, but also superposing and gluing together, the idea of gluing solutions appears in that paper. So we're going to start first by gluing together the solution A and B. And I'm going to show the profile in a minute, but the result that we have for these non-symmetric waves. The non-symmetric waves, in fact, bifurcate from the point A and B from these two curves, which are these broken curves. And these broken curves are curves, in fact, which correspond to symmetric waves, multi-packet symmetric waves. And this wave here starts from one point on the red curve, from a symmetric curve. It goes up all the way up to there. Then it turns and come back and end up again into symmetric waves. In all the calculation that we did, it always went from a symmetric waves to another symmetric waves. Now we try now to make that a little clearer, so I'm going to show again that picture that we have there. By the way, we have a blow up of this region here to try to illustrate what we get. So you'll get the same picture on the next slides here, but in black and white. And here you get a number of profiles of the non-symmetric wave. Well, what you get here in the first picture is in fact the two solutions, the two symmetric solutions corresponding to the point A and B. The two waves were traveling at the same speed. So we use these two things and we glue them together. We glue them together, in fact, at a point so that it would be something smooth. The profile would be smooth, and the slope would be smooth. We glue the elevation wave and the depression waves, and we put that as an initial guess in the Newton iteration. And the result after that comes, in fact, to I believe this one that we get there, to a wave which is this one. So this is a converged solution of the Newton iteration, and you can see that it is a wave which doesn't have a symmetry. There is no vertical line with respect to which the wave is symmetric. So it's a different wave than we.
These correspond to 3 or 4 in your plot?
Yes. This one, which is this one, yes, it corresponds. So these two pictures that we have in here correspond to 3 and 4. And the two that we get there, here and here, correspond to 5 and 6.
Jean-Marc, I have a
Yeah.
Which is you're doing a hard problem, which is you're taking two very active, but pretty localized solutions and putting them right next to each other, and they're asymmetric. But couldn't you also take a huge domain, put one over here that goes up, and 20 miles away, put another one here, goes down, and converge faster, and that's an asymmetric wave? Maybe a little less interesting.
I mean, in principle, when they're far away, it didn't always converge.
Really?
Yeah.
Huh.
I think I'm correct about that. Yeah. It's quite sensitive to. You have to play with the initial gas. First cooked up the initial gas, and then of course we said that when we glue them together, we end up with one of those waves here, which is a point on the curve, and then you have to use the continuation methods to generate, in fact, the branch of solutions. But here you have a branch which go up, a branch to go down, so we have solutions which are very close to each other. So you have to move very slowly the parameters. Of course, change the parameters when you get a turning point, and so forth. And the end of it, which are in fact the points, which are these 2 points there that you see on the blow up of these 2 points here, which are on the broken curve, are in fact symmetric waves, which is the end of it. These are these 2 waves that you have there. These are symmetric, and one is an elevation one, and one is a little bit of a depression wave, but these one are symmetric. So the whole thing bifurcates from these symmetric waves that you get there.
So points 1 and 2 were on your original plot of symmetric waves, and those dashed curves were on your, it was like 10 slides ago, of your big spaghetti
It's
bowl.
possible that in continuing the curve we would get to that, but these are symmetric waves, so they would be, or the branches bifurcate from the fundamental. Yes, branch.
Does anything stop you from taking more than 2?
Computational, if you put only 10,000 points, so you put 3, you get to. Yes, there's a lot of different waves, and you could probably do it with 3, with 4.
Well, you just need a spot where you have 3 waves. But I mean,
Sometimes you can get 3 waves which travel at the same speed. We could try to play that kind of games, or 4, or. Yep.
As long as you have graduate students.
Yeah. Well, you put them. You put them. Together, it's no guarantee that it's going to converge, because it's not a simple superposition. Hmm?
Asymptotically, at least, you can do it.
You can do it with a fifth, yeah.
Time, so it suggests that it's probably.
To any number, probably, yeah.
I think the bifurcation diagram you're getting up there in the blown up is very similar. It was a long time when we did it. I think it was 97.
Yeah.
It's very similar.
This
what
case,
we
to
were
the point
getting.
A and B, is of course similar, because
Very
it's built with an elevation wave and a depression wave, which is what we were doing.
Yeah.
Now the one that I'm going to show, which is to combine 2 elevation waves traveling at the same speed, that will be a little different, because you don't get that for the 5th order KdV.
Is that right?
I think so. Yeah. You don't get that complicated structure that you get there.
If I remember correctly, the important thing here is asymptotically how you slide the envelope relative to the carrier.
Mm-hmm.
So the 2 having the same speed, originally the unperturbed ones, is not the key idea. Now I can see it numerically why you want to do it that way, but asymptotically it was a different thing, how you slide the envelope.
Yeah, it's a different
If I
asymptotic.
remember correctly, we did elevation and elevation,
Okay, I'll have to.
but it's a long time.
Yeah,
Okay.
I'll have to check in
All right.
your JFM paper on that. Yeah. So what I'm going to do now is to show one with 2 elevation waves, which are in fact the points C and D. They're quite close to each other. If you have a blow up, and we're going to try to play a similar game. So you can see here that the situation is much more complicated. But again, what is similar is that you have these branches, this broken line, the red one and the blue one. And in fact, the branch bifurcate, in fact, from the symmetric wave as before, do a lot of complicated things, and end up also as a symmetric waves. And what it does is a complicated things here. It goes up and down, and I'm not going to attempt to show you exactly what it does. It's a complicated situation here that we tried a little bit to clarify by putting some kind of blow up of what's happening along the curve. So again, same thing as in what we had in the previous case. Again, the same picture that you have there in black and white. Again, here's the idea of these two elevation waves. These are the points C and D that we're going to glue together. And then we let it run, and it comes, in fact, to a solution. I believe that it is this one after running the Newton iteration, which is clearly a wave which is non-symmetric that we obtain in this case. And then we have complicated structure, complicated waves that we get in here. Yes. And we can continue, of course, to play this little game. And the last example that I'll show in 2D will come from a superposition of the two elevation wave E and F. So again, we go to this particular structure. If in fact the thing goes here in a complicated way, that again I'm not going to describe, but it also again start at the bottom. You can see that on the blow up, to start with the symmetric waves, go all these complicated things and end up again with another symmetric waves. So again, a similar type of things. This is the two waves that we glue together. Then it goes and it generates, I believe, a wave which should be one of those, I believe, that we have there, or close to. In fact, it comes to something which is up, which is close to this one, I believe. And then it evolved. This wave flow looks the same, but in fact the difference, these crests at a slightly different height. And ultimately, it ends up, as we said, with the symmetric waves. Okay, so I think that...
Mark, I have another question.
Yeah.
Again, another completely naive question. Is that where you glue is a little bit arbitrary. You just adjust it to be nice. Is it possible that there's an extra phase factor that if you glue it slightly differently, you get a slightly different solution? I'm just wondering if this, because there is some sliding freedom of one solution against another.
You might converge on another branch of solutions.
Or I'm thinking of a parameter family of solutions for each one of your branch.
I don't think so. I see these solutions are isolated because, I mean, we do them in a very accurate way. And if they were not isolated, you wouldn't get a convergence in the Newton iterations. So we have the right number of parameters. But these are just example of three waves, and it's three families of waves, and there are many other families that you can generate. Yeah.
So that would mean if you would change the phase, that you would converge to the same solution. That's what you would say.
It could converge to the same solution or generate another branch. Yeah. Yeah. Would you agree with that? Yeah. Yeah. Hydroelastic waves, Gao Tao has been trying to do a similar things for the wave with the elastic sheets, maybe with both infinite and infinite depths. This is work which is in progress. This is just one of the profile that he sent me to show that something similar, in fact, occurs in the problem of the hydroelastic waves. Now I want to talk now what we can do about three-dimensional waves, which are, of course, waves that we heard about from, well, today from Emilien Parot. And as Emilien described, the three-dimensional waves, we can also calculate them by boundary integral equation methods. He described it by boundary integral equation method based on Green's function. And the basic one, we did, in fact, calculation like that quite a number of years ago, 2005, with Emilien and with Mark Cooker. And these are example of waves. This is a three-dimensional depression waves that we computed at the time. So the wave, again, have decaying oscillations, but decaying oscillations in the direction of propagation, and monotonic decay in the direction perpendicular to the direction of propagation. Don't see it very well. If you cut it in half, it looks a little better. And again, cut in half, that's an example of an elevation waves. Of course, to do that, you need to put a lot of grid points, and it's quite hard to find very accurate solutions. And if to compute this new non-symmetric way, we needed in 2D something like 10,000 mesh points, it would become hopeless in the three-dimensional case. Three-dimensional case, you reduce it to something on the plane. You would have to solve system with, I don't know, 10 million equations with 10 million unknowns. It takes forever to do that. And what we were interested is to see qualitatively if we can get something similar in the three-dimensional case. And to do that, we simplify our life by using a model equation, which is a model equation derived by Akers and Milewski. And I'm not going to go through it because it was described by Aquilas yesterday. You might recognize this equation that you have there. U as a function of x and t, that is the time dependence, is the elevation of the free surface, is the equation that he was using with two simplifications. What he was using yesterday, there was a forcing in that equation, and there was also a term to model dissipation. This is not that, it's the original model of Akers and Milewski, based, in fact, what was the idea, is based to have the property of the linear dispersion relation expanded near the minimum that you have there, and also to fit it with the NLS, and in fact by fitting in the NLS that give the numerical value of that coefficient alpha. So this is the model of yesterday, and of course that's something which is much easier to solve. The H here is a Hilbert transform, and this is what we have been using. Now, that's okay, that's a model. At least what we should know, it's not an exact model, it's even not an asymptotic model. How good is that model? Does it at least describe qualitatively the waves? Now to check that, well, the only thing we have is we have very accurate solution for two-dimensional waves. So we use that particular model and recalculated two-dimensional waves. So that is a comparison of, in fact, against the speed versus the amplitude, what we had for elevation waves. You might recognize this curve. That is a curve in which we have the point A and B and so forth. And the solid curve is what we have there with the model equations. And the broken curve is what we have with the full Euler equations. So you can see qualitatively it's the same thing. Of course, it doesn't fit exactly, but at least qualitatively, it is the same kind of thing. This is again a comparison with the energy, but here this is along that particular branch, a comparison of the profiles. The solid line must be the one with the model, and the broken line must be the one with the Euler equations. The amplitude are not exact, but qualitatively is the same type of profile. So what we do in here is in fact to compare in this point that you have there, which is a model equation, with the full Euler, and this point here also with the full Euler. That is what generates these two pictures that we have there. And qualitatively, that's rather reassuring, so we could get some idea of these three-dimensional waves that we in fact calculated in a method which is similar to what we use in 2D. So this is still for symmetric waves, but this time elevation 3D waves. This is the energy versus the speed. Maybe that would look more familiar if I put it with the amplitude versus the speed, and you get again this curve. It's bifurcated from square root of 2. It goes up, and then it has a turning point here, and then it goes again. We get again this complicated kind of picture.
Sorry, that's for the model again?
This is for the model. And but now we move to 3D.
This is a 3D model.
This is a 3D model. We use the 2D to get some confidence that the model is doing reasonable things. And now we're going to got some confidence. We're going to use the model and see what we can get. So of course there is also a branch of solution which has a depression wave. And again, we can get a depression wave and an elevation wave traveling at the same speed, and also several, in fact, elevation waves, we can also travel at the same speed.
And you're only allowed to travel in the x direction?
Yes, that's right.
You assume a symmetry in the y-axis?
Yes, in all the solutions, you could ask them, the non-symmetry will come in the x direction. You could ask the questions, could we get waves also with a non-symmetry in the y directions? We don't know, we tried, but we never
But
got,
it doesn't converge.
it doesn't converge.
But it doesn't mean it doesn't exist.
Yeah. You know, when it converges, it provides numerical evidence that it exists. When it doesn't converge, but maybe we don't have the good initial guess.
Those are situations where the speed and the momentum can be different in different directions.
I mean, the reason.
You just have to expect that the speed, the direction of the speed vector, the velocity vector, and the direction of the momentum vector are different. If you make it symmetric, they will align.
Okay.
Okay. So now we're in the 3D. What do we get? So this is along that branch, an example of a 3D still symmetric waves computed with a model. Here is another one. There is I want to mention that to get the non-symmetric wave, well, a method is to group, as we did before, two solutions using an initial guess and run the Newton iteration. There is another approach that was developed by Zan. It is another clever way to do it, is to start with the two-dimensional calculation. There have been analytical results of Gross, Aragus, and Sun, and most recent numerical result of Milewski and Zan, which in fact connect through branches the two-dimensional solitary wave and the three-dimensional solitary waves. This idea is that there are also solutions. So the three-dimensional solitary waves are waves with decaying oscillation in the direction of propagation and monotonic decay in the other direction. There are also waves with decaying oscillation still in the direction of propagation, but which are periodic in the direction perpendicular to the direction of propagation. And this family of waves go from the 2D wave to the 3D waves in the way that I'm going to try to illustrate this transparency. So this is a symmetric wave that we get there. It's a 2D waves, so it's any plane in that direction perpendicular to the screen is all the time the same thing. So that's a way to represent a two-dimensional waves in 3D. And then from this, you can then go to waves which are then periodic in the direction perpendicular to the direction of propagation, is just having one wavelength in that particular direction, and then you move along that branch, and then you move along that branch, and ultimately you end up with a three-dimensional wave. So that gets another way to compute the non-symmetric wave is to try to do the same thing. Start with a 2D non-symmetric waves and go through that process, and you end up at the end with a three-dimensional waves. So you start with a non-symmetric wave, which is 2D, and then you move along that type of branch, compute the periodic waves, and at the end, you end up with a 3D non-symmetric wave, and that approach works also.
But is it then symmetric in the y direction or not?
Yes, everything is symmetric in the y direction.
So you
But the non-symmetric, as you're going to see on the profile, is in the x direction.
you could also have a wave which is non-symmetric in both directions. In principle.
In principle, but they haven't been found, and they haven't been found analytically, they haven't been found numerically, so it's an open question.
All right.
Yeah. So this is a typical kind of thing that we've been doing. This is for the 3D case. And again, we get now the branch of non-symmetric waves. As before, we found that they bifurcate from symmetric waves. And you move along the branch, for example, starting from that point I, you move along there, and then you end up again with asymmetric waves in the opposite direction. And that's an example of a computation of such waves, which is non-symmetric. 3D wave with the non-symmetry being in the direction of propagation, which is the x direction. In the y direction, it is symmetric.
Do you have an illustration of approaching the symmetric bifurcation point? How does that look?
Well, we had that in the 2D case.
Looks like the 2D case.
Yeah, but then I can go back to this. Let's see what our 2D case. Yeah, you see it a little bit. You move along the branch, and then
That's symmetrized.
yeah, it's symmetrized. It gets less and less non-symmetric, essentially. It's all continuous, all smooth. Oop, 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 oop. Just to illustrate a little bit better the non-symmetry in the x direction, by just cutting the wave, in fact, well, in the plane y equal to 0. And of course, if you do that, what you end up is profile which looks a little bit similar to the 2D one, but they're not two-dimensional waves. So this is in fact doing the process starting with 2D non-symmetric waves, and then going through the periodic waves, boop, 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 and then end up at the end with a 3D waves. So we start with the non-symmetric 2D waves, compute the waves which are periodic in the direction perpendicular to the direction of propagation, move along that branch, and end up with 3D waves. Just for fun, these are similar pictures to what you've seen before, putting some color to feel better. So, conclusion of this, we've been presenting new non-symmetric waves, but they were done in the 2D case for the full Euler equations, and we've done also similar result for 3D waves, but by using a model equation. How am I doing as a time?
15 minutes.
15 minutes. Well, I'll mention something on stability, just a few minutes. That would be, what about the stability of all these waves? Well, the basic symmetric waves, the elevation and the depression waves, the depression waves up to moderate value of the amplitude are stable to longitudinal perturbation. The elevation waves for small amplitude is more complicated. They are unstable to longitudinal bifurcations. You move along the branch, then they become stable again, and if you continue to move, they become unstable again. So the result, the stability of the depression wave, and also part of the thing that I said of the elevation waves, were first shown, I believe, by Young and Akilas a number of years ago. But then we also studied that numerically with Zahn and with Paul Milewski by using a time-dependent code in 2D and following the dynamics. So what we found in that case is that when the elevation wave is in fact unstable, if you do a time evolution, then in fact the elevation wave evolves into a depression wave in the dynamic, which is then, it evolves into a stable depression wave. The new thing now, we put the branch of solution of the elevation wave, which go much further, and then we found again that that's a new result in it, that the wave, the elevation wave, is first unstable and then stable, but get again unstable. That is the thing that we got there. So that's just a computation here, increasing the time that we get there. showing in fact a 2D that we get there, in fact, elevation wave, which is stable. Moving that, when you have the elevation wave, which was then, as we said, unstable and then stable and again unstable, this is what happens to it as a time evolution. You get there, and then the waves, in this case, break into 3 depression waves. So this is for longitudinal perturbation. We also made studies, in fact, of the waves and study, in fact, the stability to transverse perturbation that we can do. This is here a study for 2-dimensional waves that we get there. And then it's unstable. Everything is unstable to transverse perturbation, and then it evolves to this, and then break into different waves. And then I put here just a picture of what's happening to transverse perturbation, but for a 3-dimensional waves. It's more freedom in that case. So this is the waves that we get there, and then it evolves in here and ultimately become two depression waves. So I think I'll stop on this with some result of time dependent at the end. Yes, Anna?
2 questions, if I may. First, so all the stability evidence was numerical? Also, your result as well?
Essentially, it become numerical. Well, sometimes it's a small perturbation, but you have to solve it
And it was all time
numerically because you're studying the stability of something which is not known analytically.
But it was time evolution, right? It was not calculation of the spectrum or anything?
Yes, that could be. They would be part by the spectrum, putting exponential lambda t, and yeah.
Second question, do you know anything about asymmetric periodic waves?
Periodic in both directions.
Let's just say
Well,
one-dimensional surface, just X.
Yes, there's paper by Sophia.
Yeah, for model equation, yeah.
Also a paper by some
But
guy
this
out
is 87.
for the oil.
Yeah. So I think yes, they would be
Yes.
also
There are 2
non-periodic.
papers.
Yeah.
Also
We already got now families of solution all over the place. Just a focus on solitary waves, remove 1 parameter. But they would be, I would believe, non-symmetric periodic waves, which as the wavelengths would increase, would probably approach these solutions. Yes, Victor.
So you concentrated on the family of solitary waves which decay and infinite.
Yes.
So there are also solitary waves which have oscillating tails, which have constant amplitude and infinity.
Generalized solitary waves, yes.
A kind of generalized solitary waves.
Yeah.
These solitary waves, from physical viewpoint, are so when these tails are small, are no different from the ones you studied. So they will be radiating. They will be not steady in reality, but they behave in.
Yeah, they are physical because you get the ripples on both sides. Yes. Yeah.
So in reality, if they exist, they will have tail only on one side. They will be radiating.
Correct. Yes.
Solutions, but because the tails are so small, so the behavior will be so they will not matter. Have you looked a little bit at these solutions or not? Because they would provide you natural asymmetry. So
I certainly look at generalized solitary wave. If you go to something that you're doing now and it's radiating, of course it's not a traveling wave. It's almost a traveling wave.
yeah, so if you look into symmetric structure, then it will be traveling wave. Yeah, so with tails on both sides.
Yes, that's
and
right.
You could see the parameter space of these solutions because this would really extend the range where localized patterns can be observed.
Mm-hmm.
So,
With the tails on one side, yeah.
with the tails on one side.
Yeah, it's, I haven't done it, but I think it must have been done by.
Victor, with these with the, first of all, the oscillatory tails, these bifurcate from a different point. They bifurcate from the
That's true too.
Yeah.
point one. Second point,
The
for simple model equation like fifth order KDV,
Yeah.
we have looked into that. For example, what if you start with two generalized solitary waves and you glue them together but rigorously, asymptotically, such that there are oscillations in the middle but nothing at the
Yeah.
not possible. You can show that analytically, not possible. I don't think the rigorous async solutions which have these oscillations and they go to zero.
not traveling wave solution.
So what I could say is it's a different context. I looked into internal solitary waves with oscillating tail. And
Yeah.
I look specifically at radiating waves. And if you look into solution of Cauchy problem, these solitary waves emerge as intermediate asymptotics. They do not know about the tails. So that's and what happens at much larger times, it doesn't matter.
That's
Yeah.
fine. That doesn't contradict.
Yeah. What we were doing,
There is no contradiction
Yeah.
to what you're saying.
That's
So
right.
I'm
That's right.
looking at different tails.
what we were doing is to concentrate on really traveling waves which are non-symmetric.
Yeah. So,
But for example, if you take the problem we have there and you put some dissipations, the wave would be non-symmetric.
Yeah.
Of course, they won't be traveling waves.
So what I suggested that we could extend the range of parameters where you see the pattern. So that's it. And that might be of physical relevance.
Yeah. Okay. Yeah.
For these solitary waves, there's no way you can have the oscillatory tails because these all travel at speeds below. the mean.
Below, but you could consider the relatives of those that speed slightly above. Yeah. So and then you get it. Yeah.
Yeah. It's a different regime. It's,
Yeah. Different regime.
yeah,
Yeah.
it's,
Yeah. So,
usually, the generalized solitary waves also finite depths.
yeah, but here you could have them if you.
Yeah, we could put finite depths in the
Yeah.
problem. It's no
Yeah.
problem. Just an extra parameter.
Another way possibly to build these non-symmetric solutions in 3D. In the 3D problem, if you cook up the velocity just right, as you do perturbation theory, at the lowest order, you now get a two-dimensional null space. So you get something which has a wave vector k1 and k2. And now I believe that you can find a branch of solutions for any choice of coefficient out in front of each of those two wave numbers. So it could be amplitude 1, and that gives you the classical short-crested waves. But one could be amplitude 1, the other one could be amplitude 2, and now it's starting out very non-symmetric, and it's periodic, 2 dimensions. And so can you take the ideas that you used to take Mark's solutions, which are periodic in one direction, and sort of extend things periodic? It seems like you're taking the period to infinity. In that periodic, can you do it in both directions and now find something that's very asymmetric to the 3D problem?
No,
Possibly?
but possibly, yeah.
Okay. Question is, you know your examples, you know your constructions, the total energy is infinite, yes?
Thesis working.
No.
But there is oscillation at infinity, yes?
But here the oscillation decays. The one that Victor is talking about,
Yes,
the
yes,
generalized
yes,
solitary
yeah,
waves have an
but
infinite energy. That's
then
true.
the energy is finite, yes?
Yes.
Therefore, it is a question about critical points of the energy function, yes?
Yeah.
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 Yes, but you have two critical points, yes?
Yeah.
And then you get the third one. After elements, yes?
Yeah.
Yes. Then what about the linear stability on the spectrum of the problem? If you take your equation and linearize it on your solution, then you get some linear problem,
Yeah.
self-adjoint operator. I mean not stability like a Newtonian, a simply study of the linearized equation. And what about spectrum? You can say or not. Roughly speaking, I'm speaking about Morse index. number
Yeah.
of negative eigenvalues. Because the bifurcation of this kind it should be connected with change of the spectrum, roughly speaking, something past to the negative part through zero or something like this.
Yeah, yeah.
There is some topological reason for this.
Yeah, I don't know. Yeah, so they say.
Maybe it is reasonable to calculate this quantity and to look, calculate more things.
Mhm.
Quantity of the energy.
Would be interesting. Yeah. Yeah.
Three speakers this afternoon threatened to talk about flexural gravity waves. One of them actually did. Has anybody looked at putting dynamics on the flexuring plate so it can do things on its own? And you have interaction between two different kinds of waves?
We haven't done it, but we look at different models certainly for the plate.
How should it? Not dependent.
Yeah.
Computation.
Time dependent. Yeah, we.
Well, I'm wondering, could you do something where the plate could also get its own?
Oh, we'll move. Yeah, the change with more. Yeah, we could do that. Yeah. Yeah.
Yeah.
To get them big.
Yeah.
Well,
This will add another mode, right?
pardon?
Yeah.
This will add a separate
Yeah,
mode.
It will be a little bit like a, interfacial waves a little bit.
Yeah.
And get the two medium. Yeah, that would be possible. Yeah. Sure. This was a.
So the plate would have to have inertia. Right?
Yes.
But I expect it would be a stiff system because wouldn't a plate vibrate a lot faster than wave motion underneath it?
Yeah, who knows that?
Depends on, you have parameters that you put in and you can dial them to do what you want. It just worried me that huge plane landing on that 1.6 meter ice.
It's 300 meters. The depth of the water in 1.6 meter ice.
Oh, that was 300 meters. I was worried.
The ice is 1.6 meters, so it seems to be fine.
Yeah.
So the water is 350 meters under the.
That would make me nervous. 1.6 meters is this much ice.
But they do this sort of stuff.
Hope they're ready to take off.
We thank Jean-Marc and